Hey, welcome back. This is trig, and we're going to continue on with graphing other trig functions, the tan, cotan, secant, and cosecant. Tan and cotan they're kind of similar. They look similar, so they'll be kind of related. And then for cosecant and secant, it's a little bit like just graphing regular old sine and cosine, but you're kind of piggybacking in a weird way. All right, so that's the idea. That's what we're up against here in this section. I'm going to try to produce a similar procedure as what we had in the previous section with cosine and sine. So we'll look at the amplitude and then kind of look at a quasi-period, and then finally figure out the kind of key points, right? Okay, so here we go. First, we don't even know at this point what the tan function looks like. Okay, we'll proceed as we did in the previous section and produce a table based off of the unit circle. Okay, so here's our unit circle. If you remember, tan is kind of the ratio of the x and the y of the point, the coordinates of this point. So it's cosine x comma sine x. Tan is cosine over sine. So basically, if you have 0 degrees and you're looking for the tan of that, you're just going to take the ratio of 1 over 0. And in our case, of course, 1 over 0. In our case, that'll be it's sine over cosine. So let's just remind myself here. So that would be 0 over 1 in that case, and the output for tan would be 0. Okay, so we want to make a table and then plot it in the xy plane. So here we go. There's going to be x, which represents an angle, and then tan x. Okay. And we'll start with 0. Or actually, we're going to start at negative pi over 2. So that would be this angle right here. And maybe we should label these points. Okay. So starting at negative pi over 2, we have negative 1 over 0. It's undefined. Okay, so we hadn't seen that before in the other graphs. What undefined means is we have division by 0. Graphically, that'll be an asymptote. So there's an asymptote at negative pi over 2. Okay. Let's then move to negative pi over 4, which would be have this terminal side right here. That point there, if you remember from our previous discussions, is at radical 2 over 2, comma, negative radical 2 over 2. And of course, then for the tangent of that, we'll just have negative 1. So negative 1. With the angle of 0, we'll have 0 over 1. That's kind of where we started, 0. And then we'll go by pi over 4s. Okay, so let's pretend this is pi over 4 here. And the point on the unit circle there would be this time root 2 over 2, root 2 over 2. So the ratio of sine over cosine, root 2 over 2 divided by root 2 over 2 is just 1. And then moving to pi over 2, right here, you have 1 over 0. So again, it's undefined. So you have another asymptote. And that's kind of the characteristic of these tan graphs. You have asymptotes at odd multiples of pi over 2 in the end. Okay. Anyways, let's keep going a little bit. So 3 pi over 4, which is located right here. The terminal end is right here. That point on the unit circle would be at negative root 2 over 2, comma, root 2 over 2. Sorry, I'm kind of smushing that in, but the end result would be negative 1. And then we're at pi. So we'll have 0 over negative 1, which is 0. And then we are at 5 pi over 4. So in that case, again, you're looking at one of these ratios of, in this case, negative root 2 over 2, comma, negative root 2 over 2, which of course is just going to be 1. And then 6 pi over 4, which is 3 pi over 2, which will have the same value as negative pi over 2 because of the periodicity of the function. This thing just goes back to being undefined. Okay? And that's really the big and the small of it. Let's go ahead and take a look at this thing in the xy plane then. And, where do we start? We started at negative pi over 2. And as promised, there's a vertical asymptote right here. And then it's at negative pi over 4, which is halfway in between negative pi over 2 and 0. You have negative 1, so maybe put some tick marks on here. And then it goes to 0, and then it goes to positive 1 at pi over 4. And then at pi over 2, positive pi over 2, there's another asymptote, right? And then the pattern just repeats. So if you were to fill in more dots, what you would end up seeing then is this kind of behavior. It kind of looks like a cubic, but it's not. It just keeps on going up in that direction. And then it'll repeat itself. So you can kind of think of it as having 4 main parts. It's just now the period, instead of being 2 pi, the period is 1 pi. Okay, so if you measure the distance from pi over 2 to negative pi over 2, that's just 1 pi, right? So, whoops, 1, 2, 3, whoops, I need another little tick mark there, sorry. So again, doop, doop, and then doop, which looks like this. And it just keeps on repeating itself. So on this side, 1, 2, 3, and then another of those guys. So 4 main parts that are there. And it looks like this. And just repeats all along the x-axis. Just keeps on repeating. So the domain and range. So the domain is a little weird this time, right? So the domain, there's issues at odd multiples of pi over 2. Right? So this would be 3 times pi over 2. 1 times pi over 2 is right here. Negative 1 times pi over 2. Then back here we have negative 3 times pi over 2, 5 pi over 2, 7 pi over 2. All of those are asymptotes. So I'm not going to put it in interval notation. I'll just say the domain is all reals except odd multiples of pi over 2. Okay. One way you can kind of write it would be something like 2n plus 1 times pi all over 2. And then if you let n be one of the counting numbers or the negative counting numbers or even 0, this would, so n is, dot, 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 negative 3, negative 2, negative 1, 0, 1, whoops, 2, 3, dot, dot, dot. If n is in that set of numbers, then this object that I just put in the parentheses, maybe I should put it in a different color, like red or something. This object right here will give you odd multiples of. So there's ways to write it. It's just we don't have time to kind of develop the notation. So anyways, there's the domain, a little weird. The range is all real numbers. You can see kind of y values for these points. They're going from 0 all the way up to infinity, and then 0 all the way down to negative infinity. So the range, negative infinity to infinity. And then finally the period. Like I was saying, you just find the distance between pi over 2 and negative pi over 2. So you subtract them, and you get pi over 2 plus pi over 2, which is 2 pi over 2, which of course is just pi. Okay, so let's start working with graphing the variations of the tan functions. So graphing, and we just go all at once with this a tan of bx minus c. I don't think they care about the shifted versions, but just like in the previous section, if you do have to do a shifted version, just draw the original without the plus d, and then move up or down according to the D value. Okay, so anyways, let's look at, this is checkpoint 1 in the book. And they want us to graph y equals 3 tan of 2x. Okay. So first off, the amplitude value is the same. It's just the absolute value of a, which in this case is 3. And how the amplitude kind of change these things, it'll stretch it out. In particular, the amplitude will change these points right here and right here. Okay, so see how they're kind of at -1 and 1. If you have an amplitude of 3, what's that going to do? It's going to move that green dot up to 3. Okay, it'll just move it up, or in this case, down. Okay, so it's kind of like stretching it out. Okay, so that's what will change there. Then secondly, sort of dealing with the period and the phase shift type ideas. What you're going to do now, instead of going from 0 to 2 pi, you're gonna take this thing and wedge it in between -pi/2 and pi over 2. Oops. And you can't include, like, you can't write like I did right there. I accidentally wrote less than or equal to. You can't technically do that because of the asymptotes. So what you're doing is writing less than, and then you put pi over 2 on the other side, and then solve for x. And that'll give you the interval for 1 period. So in this case, we have to multiply everything by 1/2 to solve for x. And you end up with -pi/4 less than x less than pi/4. So the length of the period then is just the difference of these two values on the endpoints. And of course, that'll be pi/4 plus pi/4, which will be 2 pi/4, which will be pi/2. Okay. Then finally, for the key points, again, we'll need 4 of them. It's just the beginning point and the end point are asymptotes. So there's asymptotes at -pi/4 and pi/4. But we want to, move through the middle. So it's going to be -pi/4 plus the period divided by, what did we say, 4, right? Plus, so the formula is always kind of the beginning plus period divided by 4. And so in this case, it'll be -pi/4, and then you keep moving by pi/2 divided by 4, which is the same as pi/2 times 1/4, which means we're going to start at -pi/4 and then move over by pi/8. Okay. So for your tick marks, you probably want pi/8. So you're going to start at -2 pi/8, just finding a common denominator, and then move by pi/8. Okay. Okay, so let's put it all together in our graph. Okay. So I'm starting at -2 pi/8. And then the key points are at every pi/8. So I wrote -2 pi/4. So this will be -pi/8, 0. Sorry, I had to sneeze. Sorry. And then 0, and then 1 pi/8, and then 2 pi/8. And again, the asymptotes are at -pi/4 and pi/4, which is the 2 pi/8 and -2 pi/8. So you have this picture. If you just want 1 period, then for the amplitude, you're messing with these quarter points, right? So at -pi/8, you're going to be down to -3 instead of -1. So you have a point there. Then you have this point in the middle, and then you go up to 3 right here, and connect the dots, sort of. There's an ugly looking tangent function there. Just made it worse. Okay, so let's kind of see if I can pull this off. So it should kind of have this concave. I just can't do it. I can't pull it off. It should be kind of bowl shape down the entire way up until here, and then it goes bowl shape up. So like a parabola, a downwards parabola in this region, and then an upwards parabola in that second region. Okay, that's kind of the shape, and it kind of looks like it collapsed. I just can't pull it off for whatever reason. Okay, so that would be one period. If you need more periods, then 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8. So that'd be another asymptote there. And then you could have some more points, dupe, and then kind of just zoop in. Again, my tangent function looks crummy, but that's the idea. Okay. Let's look at one more where we have this time sort of a phase shift, quote unquote phase shift. So this is checkpoint 2, and we have y equals tan of x minus pi over 2, and we want to do 2 periods. Okay, so first again the amplitude here is just 1. Secondly, then the period and the phase shift, so to speak. I don't know if the book uses the words phase shift in this context, but just for the sake of sanity, I'm going to use the same words as we introduced before. So again, what you're doing is kind of taking the guts of the function, and for tangent, we have to wedge in between negative pi over 2 and pi over 2. So we need to solve for x then, so we're adding pi over 2 to all 3 sides. And we have 0 less than x minus pi over 2 less than pi over 2 plus pi over 2 is just pi. So we can see the period. Whoops, and I forgot we have to get rid of this part. The period is just the length of that interval. So the period is pi minus 0 or pi. And then our phase shift, or you can think of it as your kind of new starting place, start at 0. Right? Okay, and then finally the key points. It's always going to be your starting point plus your period divided by 4. Okay, so let's go at it. We want 2 periods starting at 0. So 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is pi, which is where our asymptote is. And there's an asymptote here at 0. Amplitude is just 1, so our key points, looks like that. And then, so this is pi over 4, 2 pi over 4 if you wish, just pi over 2, 3 pi over 4, and then 4 pi over 4 is just pi. And then we need 2 periods, so I need another one. So 5 pi over 4, excuse me, 6 pi over 4, I am falling apart, 7 pi over 4, and then 8 pi over 4, which of course is just 2 pi. And then there'll be another asymptote there. Get your key points, there's 3 of them. And then finally try to do your curves with the nice concave down and concave up. Concave down, concave up, and there's 2 periods for your enjoyment. Okay, and next, moving on to cotan. Cotan, very similar to tangent. It's just going to be kind of shifted. So the graph of cotan y equals cotan x. Again, we can work with the unit circle and go around every pi over 4. This time we'll be starting at 0, so the period this time is going to go from 0 to pi. So when you do kind of your second step, instead of negative pi over 2 to pi over 2, you're going to be going from 0 to pi. And you can remember it due to the fact that cotan is really cosine x over sine x. And sine is 0, at 0 and pi. Those are the places where you have the asymptotes. Okay, just like back here for tangent, tangent is the same as sine over cosine. So cosine is 0 at pi over 2's, right? So you're going to have the asymptotes at negative pi over 2 and then pi over 2. Hopefully that kind of helps you remember. I don't know. Anyways, let's go ahead and kind of work with the unit circle in order to obtain an idea of the picture. And as promised, we are going to be going by pi over 4, starting with 0. Okay. You have the same coordinates as before. The first coordinate at 0, at the angle 0, is 1 comma 0, and cosine over sine will be 1 over 0, so that's undefined. And then at pi over 4, it'll be root 2 over 2 divided by root 2 over 2, which of course is 1. At pi over 2, we'll have 0 over 1, which is just 0. At 3 pi over 4, we'll have negative 1. At 4 pi over 4, we'll have undefined again, right? And then it's just going to start repeating. So at 5 pi over 4, we have negative root 2 over 2 all over negative root 2 over 2, positive 1, then it'll go 0, and then negative 1, then it'll be undefined again. So going to the xy plane and kind of thinking about the graph of this nonsense, this time we have an asymptote at 0, pi over 4, 2 pi over 4, 3 pi over 4, and then pi. And then, so this is pi over 4, 2 pi over 4, which is just pi over 2, 3 pi over 4, 3, 4, 5, 6, 7, 8 pi over 4, it's right here. Amplitude is 1, so it starts at negative, it starts at 1, so that's another weird thing. It goes from positive infinity to negative infinity in this case, as opposed to like starting from negative infinity and then going up to positive infinity. Okay. So positive 1, you could read that off the chart. At pi over 4 is positive 1, and then it goes 0. And then it goes 0, and then it goes negative 1, okay, and then it just repeats. And the graph is like this, so it's concave kind of up, and then it goes concave down. So it's like an upward shaped parabola, and then a downward shaped parabola. Okay. And then it just repeats. And there's multiple, at every multiple of pi, there's going to be an asymptote. We can go in the other direction as well. Okay, so the domain issue then, the domain, again, it's kind of weird to write out. We'll just say all real numbers except multiples of pi. If you wanted to write like a formula for that, like we were doing last time, you could say n pi, where n is one of those integers, so negative 1, negative 2, 0, 1, 2, 3, 4, negative 3, negative 4, those numbers. Okay, that will give you a formula. The range, again, is negative infinity to infinity. The period, just divide or subtract the location of 2 consecutive asymptotes, so pi minus 0, and the period, just like with the tan function, is pi. It's just kind of our position is from 0 to pi, right? So 0 to pi for cotan, negative pi over 2 to the pi over 2 for tan, and yeah, then 0 to 2 pi for sine and cosine. So anyways, let's dive in here and look at graphing variations of this monster. So we'll have y equals a. Let's make sure I'm recording. I always hate it when I get in there. It turns out I haven't been recording. Where's my record? Okay, we're good. Sorry about that. Okay, so graphing this thing, y equals a cotan of bx minus c. So it works just like before. This is example 3 in the book. In particular, we have y equals 3 cotan of 2x. Okay, so first the amplitude. That's just the number in front of cotan, absolute value of it. Secondly, then, kind of your period and your quote-unquote phase shift. Like I said, I don't know if they're still using phase shift as that might apply only to sine and cosine, but I'm not sure. So this time, the period and phase shift, you find that by wedging the guts of the cotan, which is 2x, in between 0 and pi, the asymptotes. And then you solve for x. So in this case, we have to divide everything by 2. 0 by 2 is 0. 2x by 2 is x. Pi divided by 2 is just pi over 2. Okay, so we can see the period is pi over 4. There's no phase shift, so it just starts at 0. And then finally, for your key points, you're going to start at 0, and then you're going to add in pi over, 4 over the period over 4. So the period is pi over 4, and then divided by 4. So you're going to have 0 plus, what did I screw up? Pi divided by 2 is pi over 2. I'm so sorry. I'm going insane. It's the pandemic. I haven't been out of my house in a year. So, okay. So, pi over 2 over 4 is the same as pi over 2 times 1/4. In other words, we're going to start at 0 and move by pi over 8. Okay. Okie dokie. So let's go ahead and try that. I think we need 2 periods. And again, we're starting at 0. So there's an asymptote at 0 and moving by pi over 8. So 1 pi over 8, 2 pi over 8, 3 pi over 8, and then 4 pi over 8 is, your pi over 2, and that's where the second asymptote will live. 4 pi over 8, 5 pi over 8, 6 pi over 8, which is 3 pi over 4 if you wish, but I'm just going to write 6 pi over 8. 7 pi over 8, and then 8 pi over 8, which is just pi, and we have our second asymptote. And 2, 3, we need our key points. So remember, cotan starts out at positive and then goes negative. So positive, 0, negative, and then it's parabola shaped up, followed by kind of parabola shaped down. Okay, they call that concave up in calculus, and then concave down. Okay, so that's the spiel. If you need another, period, you can go in the other direction. 1, 2, 3, 4. So negative 2 pi over 8 back here, and then it's pretty simple. It's just like it's kind of like riding a bike. You have to do a whole bunch of examples, and you kind of remember it. And hopefully I've given you a procedure which is kind of consistent. So if you just kind of have the procedure down from the cosine and sine, you could do this graph kind of easily. With the exception, they got to now remember it's a different kind of period, and we have these asymptotes, and it starts tall and then goes small. All right. So, anyways, let's move on. Let's look at now cosecant and secant. So graphs of y equals cosecant x and cotan x, or whoops, secant x. Okay, so this time I'm going to approach it a little bit differently. If you remember, what is cosecant? Cosecant is really 1 over sine. So we know there's some sort of relationship between cosecant and sine, and the graph reflects that. So what's going to happen is basically just graph sine of x, right? So sine of x, its period is from 0 to 2 pi. And let's get a little bit more of it to show. If we graph it on its amplitude, it's going like that. It starts at 0. And I'm just going to dash it in, because this isn't the graph of cosecant. And it goes on forever. Okay. And then it goes down and back up. Right, so what's happening every time sine of x hits 0? Well, cosecant of x then will be 1 over 0, and you'll have asymptotes. So whenever you see the sine function hitting the x-axis, there's an asymptote there. Okay? So there's going to be an asymptote there, there, and there. Okay. As the numbers get really, really small, as they're fractions, you're going to have stuff like 1 all over 1 over 100, right? So for an x value maybe sitting close to an asymptote, like right here, the y value is going to be small, like 1 over 100. So, you know, cosecant is going to be 1 over 100. Because it's 1 over sine, right? And what happens in that is it becomes really big. When you divide 1 by 1 over 100, you get 100. So what's happening is that the reciprocal relation between cosecant and sine causes your graph to be really, really big next to those asymptotes, okay? And then it'll get closer and closer to 1 as sine x gets closer and closer to 1. So when sine is equal to 1, cosecant is also going to be the same thing, and you're going to have that right there. Then as we approach that asymptote, your y values are going to get super small, and so the reciprocals are going to get super big, and you're going to end up with that picture. For the humps that go below the x-axis, the numbers will be like negative 1 over 100. So over here on the side, for cosecant, you're going to have 1 over 100, but the bottom's negative. So when you take its reciprocal, you get something really big negative. In other words, the values are going to be way down there, and then they're going to go up to 1, and then they're going to shoot downwards. Okay? And then same for over here. So you may have heard me say that the cosecant function kind of piggybacks off the sine function, and that's what I mean. You're just going to draw out your sine function with the period and all that jazz, and then to get cosecant, you're just going to kind of draw these U-shaped kind of paraboloid type objects on top of the humps with asymptotes wherever the graph passes through the x-axis. Okay? And that's really it. All right, so the domain here, then, again, we have this issue with asymptotes. So the domain will be all real numbers except multiples of pi. Okay, so all reals except multiples of pi. And that's because sine is 0 at multiples of pi. And that's what, cosecant is 1 over sine, so you'd have 1 over 0 at those places, and those are the asymptotes. The range is kind of weird too, right? Because there's this huge gap in the y values. So the range is, to describe that, it looks like it's going from negative infinity all the way up to negative 1, including negative 1. And then it jumps, so there's a hole there, so we'll replace that with a union symbol. And then it's going to go from 1 here to infinity, and then it just keeps repeating itself as the picture keeps on going on and on, so you'll have another hump right here, etc. Okay. The period, then you just take. You can't just say it's from asymptote to asymptote. If you did that, then if you just say it's like from 0 to pi, all you would get would be this positive sort of paraboloid. So you need to also include the negative paraboloid, and what we're going to do is start at 0 and then go all the way to 2 pi for the period. So it's basically the same kind of period as your cosine and sine function, except we can't technically include those asymptotes. Okay, but we will say the period is just take 2 pi minus 0, which is 2 pi. Okay. So it's very, very closely related to your sine function. And so secant will work kind of the same way. To get the graph for secant, you're going to graph cosine, and then wherever cosine hits the x-axis, which will be at pi over 2, 3 pi over 2, 5 pi over 2, odd multiples of pi over 2, then you're going to have asymptotes in those. Okay, so pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. We have, asymptotes here. And here. Here. Well, maybe I should put in the asymptotes last. Right. So let me, sorry, completely butchered my picture. Let me draw cosine first, and then you can guess the asymptotes because wherever cosine hits the x-axis, that's where your asymptote is. Okay. Just go 2 over in that direction. Amplitude is 1. Right. So cosine looks like this. And then it repeats itself in this direction. Okay, so we have asymptotes like right here, and I should have put the cosine function like dashed here. And again, to get the graph of secant, you're just going to piggyback. Okay. So right here, part of it's right there, it's right here. Yeah, it's attached. And part of it is right here. And then it would keep on going on and repeating forever and ever. Okay. Okay. So the red part is the cosine, is the secant function, y equals secant x. Again, we can go through the domain issue and all that jazz. So the domain will be all real numbers except odd multiples of pi over 2. The range, again, is just like the range for cosecant. So we have negative infinity to pi over 2. Whoops, negative infinity to negative 1. Yeah. So negative infinity to negative 1. And then union with 1 to infinity. And the period is the same. It's just this time, for our period, we're going to go from... where do we go from? Yeah, we're just going from 0 to 2 pi again. Okay, so it'd be 2 pi minus 0, which is just 2 pi. Okay. Okay, so let's take a look at some examples. Okay, so maybe I should say that here. When you're going to your period for your period work and your phase shift work, you want to use 0 to 2 pi. And again, I don't use the less than or equal symbol because there's asymptotes that we're dealing with. And likewise here, kind of the quote-unquote period, 0 to 2 pi. Okay, so it's just like the sine and the cosine, except we exclude the endpoints. Right. Okay, so let's, like I said, let's look at some examples of these. So basically, some variations. So checkpoint 4, y equals cosecant of x plus pi over 4, so it seems like there's kind of a phase shift. So you kind of just proceed as if it was a sine function. Okay, so beginning with amplitude, the amplitude is just 1, so the value of a is 1. Then the period and the phase shift. And in this case, you're taking this x plus pi over 4 and wedging it in between 0 and 2 pi. And then subtracting pi over 4 from all three sides. It seems our phase shift is negative pi over 4. It's our starting place. And the actual period will be 2 pi again. So the period, it's still just 2 pi. And then the phase shift, or the starting point, negative pi over 4. Finally, the key points. It's always kind of the starting place plus the period divided by 4. Okay, so in this case, yeah, I mean, that's it. So let's go ahead and draw the thing. So we're going to start at negative pi over 4 and kind of move by 2 pi over 4. So 1 pi over 4, 2 pi over 4, 3, 4 pi over 4, right? 1, 2 pi over 4, 3 pi over 4, sorry, 4, 5 pi over 4, sorry, my brain is like revolting against me right now, I don't know why, 7 pi over 4, 7, 8, 9 pi over 4, okay, there's isotopes. Well, let's draw, you could just draw the sine function first. Or what are we dealing with? It's cosecant. Yeah, so let's draw the sine function. It's sort of dashed. The amplitude is 1. So it's going to go up and then down and then back up. It looks like we have kind of almost 2 periods. Let's make it an even 2 periods, right? 10 pi over 4, 11 pi over 4. Okay, get the isotopes going. Let's put them in blue. And then finally draw in the cosecant function. I'll put that guy in red. Okay. Let's look at another. So this is now moving on to, did I screw that up? Seems like I screwed it up. Maybe it's screwed up in my notes. Oh, I see what I did. I apologize. So the key point, I went by pi over 4s. I should be going by pi over 2s. I am really, really sorry, guys. I'm going to have to erase that. Okay. Sorry. Anyways, let's try that again. That's not going to kill us. So you start at negative pi over 4, and then the 4 key points are at, you have to move by 2 pi over 4. So 1, this is the first key point, and if you're drawing the sine function with an amplitude of 1, that means I should have went like this. Okay, sorry about that. And then, so this is pi over 4 to 3 pi over 4, and where it would go like that, and then 5 pi over 4. So the next key point here, and then 7 pi over 4. And I'm not going to have room to do any more, really. Oh, I'll try 7, 8, 9 pi over 4. And then 11 pi over 4. And I'll just stop it there. There'll be another asymptote. So that, you know, again, wherever the sine curves hits 0, that's where your asymptotes are. So, sorry, this one there. And then just draw on your humps. So there's going to be one right here, and one right here, and one right here. Okay. Oh, hey, what's up? Okay, so, whoops, sorry about that. I had a student come in. The last question we want to look at is a secant version. Then this is checkpoint 5, I believe, in the book. Y equals 2 secant 2x, and they want you to graph it in between negative 3 pi over 4 to 3 pi over 4. Okay. So again, you just proceed as if you're graphing. In this case, because we're working with secant, you proceed as if you're graphing cosine. So your amplitude, absolute value of 2 is 2. Secondly, then your period doesn't look like there's a phase shift, so I'm not going to worry about that. I'm wedging 2x in between 0 and 2 pi, and then I have 0, divide everything by 2, obviously, this in pi. And then for your key points, I'll try not to screw that up this time. You're starting at 0, and then you're adding in the period over 4. If I didn't make it clear, the period in this case is just, using this inequality, you take pi and subtract away 0, and you get pi. So the period in this case is pi, so we're moving by pi over 4s. Okay, we want to start at negative 3 pi over 4 for whatever reason. Okay, so negative 3 pi over 4 is back here. And I'm going by pi over 4. So negative 2 pi over 4, negative 1 pi over 4, 0, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4 should give us one complete period if you start at 0. So graphing then, and we need an amplitude of 2, graphing the sine function, let's just dash that in blue. Sorry, we're working with cosine because it's a secant. It should look like this. And then continuing on in the other direction, key points at pi over 4. So if you wanted to, key point, key point, key point. Maybe that's a little safer to do it that way. Key point, key point, key point. Okay. Get the asymptotes. So the asymptotes, again, are the places where the function hits the x-axis. And then you just piggyback for your final graph. So piggybacking this guy, and they should be kind of paraboloid figures. This one's concave up, is what they would say. This one's concave down. Okay, and I believe that is it. Okay, so negative 3 pi over 4 to 1 to 3 positive 3 pi over 4. We got it all. And okay, that'll do us. Thanks for watching, and we'll see you in the next video.